Our plan today is we're going to look at section 2.4. I will be quite frank and tell you that this is maybe the most important section in the first semester. That if we can't get the skills down here in section 2.4 and be able to do that consistently and correctly, it's going to be a problem over and over and over again as the semester goes on, like everything we're doing. In the future, most of the skills come back like, oh, I need this. And it all kind of comes back. There's like a sub-skill here in 2.4 that we're unable to do consistently correctly. So I want to preface what we're about to do here today by emphasizing that, like, this is as A of game as you have, you want to bring that today for this. Okay? So again, like, the A-est of your A game should come to play today while we do this. We will do some additional practice on this topic and on these topics. So like, it's not just today's a one-shot deal, but like, we do it right the first time and get it down the first time. That makes life so much easier. So just putting the emphasis here. So just to kind of rehash where we have been so far in chapter 2, right? We started by talking about sine, cosine, and tangent. We defined sine, cosine, and tangent using SOHCAHTOA, right? Using an acute angle from a right triangle. It's a pretty narrow definition because the only angles I can do sine, cosine, and tangent of are between 0 and 90 degrees, right? There's lots of other angles, even in geometry, that we can write past 90 degrees. But even then, like 0 to 180 is all the angles you get from geometry, right? Last class, we fixed that, right? We defined a new way of drawing angles, that standard position method, where we fixed the vertex at the x-axis, or at the origin, one arm of our angle on the positive x-axis, and we like rotate it around. And that allowed us to draw angles that were bigger than 180, that were bigger than 360, that were negative. We can now make angles of any size. What we want to be able to do now is take our SOHCAHTOA definition for sine, cosine, and tangent and extend that definition onto what we did yesterday so that we can now use sine, cosine, and tangent on angles of any size. So what we're going to do is we're going to do that translation. We're basically going to take our right triangle definition and translate it into a standard position angle definition and bridge the two. Okay? So most of what we're going to do today, like the how, is for your benefit, so you just kind of see where this is coming from. The actual what do you need is going to be it's going to boil down to some formulas. But we're going to show you how we end up at the formulas so that it makes it easier to understand what it is you're doing. Is everybody okay? So this is what I'm going to start by doing. So I'm going to just draw some standard position angle. So I fixed the vertex of the angle at the origin, the initial side on the positive x-axis. I rotate it I use the Greek letter alpha here, some alpha degrees. And then I'm going to choose some point on that terminal side. I'm going to call that point P, and I'm going to name its coordinates x1. Everybody okay with what I've done so far? Mostly nothing, right? I've just drawn an angle and grabbed a point on one of the arms. What I'm going to do now is I'm going to draw this altitude in. By doing that, what have I just made? a right triangle. Everybody can kind of see that? This is me trying to connect this back to SOHCAHTOA. So this side of my right triangle, I need to give a label to. The label I'm going to give that side is x, because when I plot this point P, how do I plot a point? I'm going to go x over, and then y up. Everybody good? Nothing tricky here, right? Now the third side, the hypotenuse, I'm going to call that r. And I know that r then is going to be equal to the square root of x squared plus y squared. Where's that coming from? That's just a Pythagorean theorem, right? Yes.
Why is it square root?
Because it's r squared equals x squared plus y squared, and we square root it in r. Is that,
yeah.
We're good? Okay, good question though. So if I look now, and if I do SOHCAHTOA, so sine is opposite over hypotenuse. But y is really a coordinate on this point. R is the distance between that point and the origin. None of those things are dependent on a right triangle. We just broke the shackles of SOHCAHTOA here. So using this diagram that we've built, we can say that sine is y over r. Y is the coordinate, the y coordinate of this point P. R is the distance of that point back to the origin. I lost that point here somehow, I deleted it. Cosine, adjacent over hypotenuse, x over r, the x coordinate of this point P, over that distance from the point to the origin. Etc., etc., etc. Tangent y over x, cosecant r over y, secant r over x, cotangent x over y. Notice that we have these extra qualifiers when we have the fractions, saying that these things can't be zero. Because all of a sudden, remember, these x and y's aren't sides of a right triangle anymore. They're coordinates for a point. Can an x coordinate be zero? Sure it can, right? Could it be negative? Sure. Can the y's be positive? Yeah. Can it be zero? Sure. Can it be negative? Sure. So we have to have these extra qualifiers, right? Like if you have a zero denominator, then like it doesn't work, it's undefined. But that's it. So this set of formulas, that's something we're going to use. Okay? That's the point of the part in the beginning. So we don't have to do that construction every time. We're just use it to create these formulas. Now remember, for the test, if you look at the notes, how many sections were in chapter 2? 4. What section are we in? 4. What's coming up then soon? Test. What do you get to use on your test, assuming you're here in class? A half sheet of notes, right? You can write on the front and back. You think a list of formulas like this might be a good thing to put on there. Now, if you're clever, if you look at this, you're like, Mr. Kulik, like, okay, I could write that down, sure, and maybe I will. But isn't this just SOHCAHTOA where you've replaced O with Y, H with R, and A with X? I mean, yes, observant student, of course. That is exactly, that's all it is. It's the same thing as SOHCAHTOA. We've just, opposite means Y, adjacent means X, hypotenuse means R, but it's the same thing. So you already know these formulas. All you need is like the this little key to how to translate opposite and adjacent hypotenuse into x, y, and r. Is everybody okay so far? This little triangle that we built, we will do again in other contexts. So we're going to give this thing a name. This is called a reference triangle. And this angle here is called the reference angle. That base angle of the right triangle that we just drew. So those things have names. We'll refer to them again later. I want to introduce them now, though. So we're just building out some vocabulary. Ellie.
Oh, the thing that cross out what's
COT for cotangent. So far, so good. Let's look at an example. So it says the point -3, 4 lies on the terminal side of some angle theta. So I'm going to just start by just drawing myself a picture. Don't really need the picture to do this. But again, like, I think it's helpful to have something to look at. So I'll draw my standard position angle. There's the point -3, 4. Everybody okay with the picture I drew? No big deal, right? It asks for the values of all 6 trigonometric ratios. Well, I have a point on that terminal side. That's my x and y. Since I have a point on the terminal side, I'm going to use my point on the terminal side definitions from above. The only piece that I'm missing, since I have x and y, is r. Remember, how did we find r? It's just the Pythagorean theorem. If you have a calculator with you, I'd like you to try typing in that square root of -3 squared plus 4 and press enter and see what you get. Because this is a place where I see students frequently have trouble getting things into their calculator correctly and getting the right response out of it. 3, 5. So the answer to this should be 5. So I think you forgot the square root, Ian.
I got 5.
The issue, if you got a decimal, is that in your calculator, it follows the order of operations exactly. So if you write -3 squared, it's going to go order of operations. Squaring comes before the negative sign. So we squared the 3 and then made it negative. That's not what you meant. You meant this. Take the number -3 and then square it. You have to type it in this way into your calculator, or at least know enough to look at your answer and be like, no. That's the hypotenuse. I cannot get an answer that's smaller than 3 or 4. Right? Remember, r is still like a hypotenuse of a right triangle. It can't be, my hypotenuse cannot be smaller than like the side lengths of 3 and 4. So you know that like, ooh, I did this wrong. Maybe I tried to do the inside part by hand. And I would hope that -3 squared, you write down 9 if you did it by hand, right? So again, watch out. This is just like an aside. Making sure that we can get this into your calculator correctly. But that's a common mistake I see students make where they get like gonzo answers. It's like, did you even look at what the answer means in respect to the problem? Like, that's an impossible answer that you just wrote down. But because the calculator gave it to you, said, well, the calculator's smarter than I am. It is not. Maybe the worst math student in the world. The calculator's not smarter than you. It's only going to do exactly what you write down. If you write it down wrong, or not what you mean, the calculator's going to do it anyway. They can't tell what you're trying to ask it to do. It can only do what you write down on it. Is everybody okay? All right. So, here we go. So sine theta is y over r. So that's 4 over 5. Cosine theta is x over r. So that's going to be -3 over 5. Ellie, what's up? Sure. Tangent theta is going to be y over x, which is 4 over -3. And remember, with a negative in a fraction, you can put the negative kind of anywhere you want. All three of those fractions represent the same thing, right? Whether the negatives at the top, the bottom, or just out front. Everybody's okay? Okay. Cosecant was r over y, so that's 5 over 4. Or you could think about it just as the reciprocal of sine. Yes, sir. Sure. Secant was r over x, 5 over -3. I'm just going to write it as -5/3. But again, it doesn't matter where you put that negative sign, right? And then our last one is cotangent, which is x over y. -3 over 4. I'm just going to call that -3/4.
So is the angle always the angle that's next to the origin that we're always trying to find? Or will it ever be like up at the top there? Like at the...
So if you're drawing a standard position angle, the initial side is always the positive x-axis, and we always rotate either counterclockwise for positive angles or clockwise for negative angles. So it's always going to be starting from the positive x-axis when we do this. Is that what you're asking?
I mean, like, are we always solving for the angle that's to like the right? Like, if you like drew like a triangle, like the altitude from the...
Right. So okay, I see what you're asking. So I know it's a carrot. What is your first name? It's not Jack. Alex. Thank you. So yeah, what Alex is saying is like, okay, if I draw the reference triangle here, I'm drawing this back to the x-axis. So like my reference angle would be down here. And my reference triangle would be out here. Yes, in certain circumstances, when we much later, like into the next chapter, we would be interested in this. Right now, no. But eventually, yes. That's what you're asking?
Yeah.
Okay. Yeah. So again, we'll deal with that more later. Today, we're not interested. But eventually, yes. Good? Yeah. Okay. So again, this is like, this reference triangle bit here is an aside for somebody's specific question about like, what if, not pertinent to doing this particular problem, but like a good question nonetheless. Everybody's okay here? Fairly easy, right? We're just plugging numbers into a formula. Worst case that this could ever happen, or worst this could ever get, is that you end up with like a radical for r, and you have to like rationalize some denominators or reduce a radical, and just like makes the arithmetic more tedious, but it still boils down to just plugging into the formula. Good? What we want to do for a moment now is predict, or talk about how we can predict when sine, cosine, tangent, cosecant, secant, and cotangent are positive or negative. Everybody's okay? This is a really, really important skill. It comes up a bunch of different times in a bunch of different places. It's going to seem really easy, and it is, but it's also like pretty easy to screw this up if you're not being careful. So again, very important skill. Is going to come back a bunch of times. If we're not good at this skill, it's going to show later on. So what I've drawn is the XY axis, and I've labeled the quadrants 1, 2, 3, and 4 in the standard way. If I think about quadrant 1, all of our x coordinates in quadrant 1 are positive. All of our y coordinates in quadrant 1 are positive. And then the r is always a distance. So that's always positive. So in quadrant 1, all of our trig functions are going to be positive because they're all x over y or y over x or x over x or r over y or whatever. It's always going to be positive over positive. Everybody's okay?
Like, what's that, like, positive or positive? Is that like, what are we referring to?
So if the x, y, and r are all positive numbers, when I write these ratios, I'm always going to have a positive number over a positive number, which means that the resulting fraction is positive. So like sine, cosine, tangent, etc. All of those, if I do an angle in the whose terminal side is in the first quadrant, the result is going to be positive. Is that?
Yeah.
Yep. And again, like if you need more detail, like stop me and ask. Like that was a great question, right? I was blowing through that, and you're like, you say, like I know what positive means, but like in reference here, like what are we saying? So like, thank you. Did everybody kind of catch Frankie's question and the clarification? Does that make more sense? If ever I'm saying stuff and you're like, I don't get it, you know, like raise your hand and help me. I might ask you some questions. I know that's scary to backtrack up to like to the point where I'm like, okay, I see where we went off the rail here. Let me help you get back. So be prepared for that, but I don't want to dissuade anybody. They're not like, not trying to accuse you of anything by asking more questions. I'm just simply trying to figure out like how far back I need to go to where that, you know, we went off track. So what I'm going to do is I'm just going to write all greater than 0. So far so good? If we move into quadrant 2, so if the terminal side of my angle is in quadrant 2, the point on that terminal side, the x coordinate is going to be negative, the y coordinate would be positive, well, and the r is always positive. So if I go back and I look at my ratios, the ones that have exactly 1x are going to be negative. Anything else is going to be positive, right? So cosine is going to be negative because it has an x, so I'd have negative or positive. Tangent is negative because it has an x, so I'd have positive over negative. But sine, that's positive because it's y over r, positive over positive. And the same is true for their reciprocals, right? The reciprocal of sine, still positive. The reciprocal of cosine, still negative. Reciprocal of tangent, still negative. So cosine, and I'm sorry, sine and its reciprocal is the only one that's positive there, right? cosine and tangent. Oh my goodness. And their reciprocals are negative. So when I write this, I'm only going to write sine, cosine, and tangent. I'm not going to bother with the reciprocals because the same thing is true for the reciprocal function. Like if a number is negative, its reciprocal is negative. Is that okay with everybody? So just to clean this up so I don't have like a million things written down here. If we move into quadrant 3, x and y are both negative, but again, r is a distance. It's a distance from the origin to that point. The distance or length is always going to be a positive value. So x is negative, y is negative, and r is positive, so I have negative over positive, so sine's negative. Negative over positive, cosine's negative. Negative over negative, that's positive. Tangent would be positive. And the same thing is true for the reciprocals. So let's go and record that. So far, so good. And in quadrant 4, x is positive, y is negative, and r, again, always positive is a length. So if I scroll back up and look at my trig functions, y is the only negative. So I have negative over positive, so sine's negative. Positive over positive, cosine's positive. Negative over positive, tangent's negative. Everybody feel good? Now, what I want to do is create an easy way for me to remember this information. Now, obviously, you can write this down on your note card for the test. That would be fine. And again, that note card is due on the review day. If you want to start collecting stuff together on your note card beforehand, if you're working on the homeworks or you're going through the notes and I mention something, you're like, that's a good thing to put on my note card. Start like a draft of it or whatever now, that's fine. Or if you meet with a tutor on the weekends and somebody helps you through stuff, like you can start on that over the weekend with them or start piecing it together as you go.
When's the review?
Probably next week. I'm not, we haven't settled on a date yet. It depends on how next class goes and stuff. You know, I kind of let that float, but probably next week is probably one either A or B day will probably be taking a test if not both. So here's what I learned when I was a student 25 years ago. So if I look at just the positives, if I look at just the parts that are positive, all, A, sine, S, tangent, T, cosine, C. And then I created like a stupid mnemonic device to remember these. And I think what we did when I was in high school that I still remember, so I guess it must have worked. We said, all silly turtles crawl. Make up your own if you want. But that's the idea. So A for quadrant 1, that means all of the trig functions are positive. S, quadrant 2, S, Sine. Sine is positive, and it's reciprocal. Quadrant 3, T for turtle. Tangent is positive, and it's reciprocal. Quadrant 4, C. Cosine. Cosine is positive, and it's reciprocal. Max, what's up? Sure, no problem. Is everybody okay with this? Going forward, it's going to be really important that we can look at the sign that a trig function has, whether it's positive or negative, and figure out what quadrants it could lie. That's going to be a critical skill, and the way we're going to do it is just using this over and over again. So that's going to happen next chapter and in following chapters. Over and over again, we're going to use this skill. Like, this is something that, like, yes, put it on your note card, but like, probably just need to like have it memorized. Like, you'll use it so much that it'll get in the way if you're consistently having to like look this up, look this up, look this up. It's just easier to have it like right there. Is everybody doing okay so far? Again, has anything we've done tremendously difficult from a mathematics standpoint? Like, the computation is basically zero. This is just like, can I look at something and say what it is? You know, like closer to a, you know, like a definition in a science class than it is to any kind of mathematics so far. We're just like building out some system that we're going to use to do problems here in the future. So let's say we want to find cosine of 150 degrees. So what we're going to do is we're going to use our new definitions that we just created in order to do this. Step 1 is going to be draw a picture. If you remember in our last class when we talked about drawing these standard position angles, I talked about that being a core skill that you're going to have to be able to do effectively for reasons like this. And the critical piece of this is making sure the terminal side is in the correct quadrant. If your picture is close, that's going to be good enough, but the terminal side has to be in the right quadrant. So I'm going to draw my initial side. This is a positive angle, so which way am I rotating? Clockwise or counterclockwise? Counterclockwise. And I need to go 150 degrees. So how far is one quadrant? 90. So I'm going to do 90 and then like 60 more. And that's going to get me like 150 total. Everybody feel good on doing that? Now notice, to draw this piece, just kind of stick it in the middle somewhere, right? Like, it doesn't have to be super precise. Like, about is good enough. There's no measurement I'm doing, just eyeballing it and going, well, 60 degrees is like 2/3 of the quadrant. I'm just going to shoot for something like that. A little more than halfway, good enough. Doesn't have to be like NASA level precise. So far, so good? Okay. I'm going to pick a point anywhere on that terminal side. I'm going to label that point P. And I'm going to leave some space because I'm going to figure out the coordinates for that point here in a moment, so I can write those in. But before I do that, I'm in quadrant 2, right? Mm-hmm. What can I say about the values of x and y there? X has to be negative and y has to be positive. So I'm going to write that in for myself right now, so that I don't forget. Okay, come on now. That I don't forget it.
Wait, can you repeat that again? How do you know?
In quadrant 2,
Okay.
So we're going to the left, so my x coordinate has to be negative,
Okay.
and then we went up, so my y coordinate has to be positive. It's also like
Yeah.
right
okay.
there too, when we wrote it down. So either way of thinking about it is fine. Frankie?
So do we always start in the quadrant one before we go into the second one?
Yes. Yeah. Everything always starts on the positive x-axis, and then either you're rotating forward or you're rotating backwards, depending on if the angle is positive or negative. But always starts on that positive x-axis, every single time. Everybody good so far? Okay. Now that I've done this, I'm going to do the same thing I did at the very beginning and draw my reference triangle. There it is. What does this angle here have to be? What would my reference angle have to be? 30 degrees. Great. How did you get that?
The apartment is 90, so 9 minus 60.
Great. The whole thing, the whole quadrant is 90. To there is 60. That piece has to be 30. Everybody's good? So what does this angle up here have to be then? 60. Aha! What kind of triangle do we have here? 30, 60, 90 triangle. Excellent. You know why that's excellent? Because the side lengths of a 30, 60, 90 triangle exist in predictable ratio to each other, right? If you go back to this guy over here, oh, sorry, this, oh goodness gracious, don't do that please. So many things. Right? We wrote that down in the 2 notes. The short side is A, the medium side is A times root 3, and the long side is 2A. So I'm going to use that right now again. So the short side is A, the medium side is A root 3, and the long side is 2A. Everybody so far so good? Now I'm going to do something unusual here because these side lengths of this right triangle aren't really side lengths. They're coordinates for that point. So to get to that point, we went left on the x-axis. So really that's a negative side length. Ooh, that seems weird. It's only because it doesn't really represent a side length. What is it really representing? The x-coordinate, right? It's really a coordinate, so it's okay that it's negative. And then we go up, so the y there is positive. And then this third side is the r. Does everybody feel good? Look at that. What do we have now? Everything we need to do cosine of 1/5, right? So if I go back to my unit circle definition, or my point on a terminal side definition, cosine is x over r. So that's negative a root 3 over 2a. Everybody feel good? Did you notice that anything about that fraction? It can reduce. What can reduce? The a's. So we're negative root 3 over 2. Everybody okay there? So we have one more step to go in our process of extending this definition of sine, cosine, and tangent outside of from SOHCAHTOA to our final form. Okay, this is kind of a transitionary step. We still occasionally use these formulas that we've created. We can do a little bit better. Because there's one piece in this process that hasn't been standardized. One piece in this process we have lots of choice on. That piece is how we're choosing that point P. So the completed version is we're going to standardize our choice of P so that the distance from P to the origin is always going to be 1 unit long. Now, instead of choosing any P, we're choosing P specifically so that that distance is 1 unit. The R will always be 1. If I collect all the points that are 1 unit from the origin, what shape is that going to make? A circle, right? And what is the radius for that circle? 1 unit. We call that then a unit circle. So if we take our point on the terminal side definitions, and R is just equal to 1, y over 1 just becomes what? X over R becomes X. R over Y becomes 1 over Y. R over X becomes 1 over X. Notice that tangent and cotangent stayed the same because they don't depend on R at all. Everybody's okay with that? What we do next is this process that we did where for 150 degrees, where we drew the angle, built the reference triangle that includes a 30, 60, 90 triangle. We're going to do that for every angle that we can build a reference triangle that's either 30, 60, 90 or 45, 45, 90, and we're going to write it down. This is the result. When we talk about the unit circle in trigonometry, this is the result. Now look at this for a moment, and it looks exceptionally overwhelming, right? All this is an exact value calculator. Okay? If you try to do sine or cosine of 150 on your calculator, it cannot give you root 3 over 2. It's going to give you 0.866, right? I guess negative root 3 over 2. It'll give you negative 0.866. To get the exact answer, without having to do all that rigmarole where we drew the reference triangle and wrote in the ratio of side lengths for a 30, 60, 90 triangle, you can use this as a workaround for that work. This someone has done the exact same process for every single one of these angles, drawn the reference triangle and figured out the points for us. So if I want to do cosine of 150 degrees, I locate 150 degrees on my unit circle. My unit circle definition says cosine is equal to x. I find the x coordinate. So cosine of 150 is negative square root 3 over 2. Done. Remember how long it took us to do the previous problem? Where we had to draw all the information there ourselves? All this is a shortcut around having to do that every single time. So in trigonometry, we're asking for an exact answer involving sine, cosine, or tangent. The tool that we're going to use is this, the unit circle. If I asked you for sine of 300, I locate 300. My unit circle definition says sine is y. The y coordinate is negative root 3 over 2. Done. It literally takes 3 seconds or less to do this. Remember how long it took to do cosine of 150? It was like 5 minutes. That's down to 3 seconds. Pretty good. Pretty good. All right, we have one final example problem. I think I've got 5 minutes left. That should be just enough time. It says, find sine theta if cosine is 5 over 7 and cotangent is negative. So my first order of business is going to be to draw a picture. Okay? For my angle theta. So if I look at what I'm given, I know that cosine is positive, cotangent is negative, and as a result, tangent is also negative. So if I go back to my all silly turtles crawl, what quadrant is cosine positive but tangent negative? It's in quadrant 4. So my terminal side needs to be down there. Everybody feel good so far? So if I take my point, what do I know about the x-coordinate? It's got to be positive, because it's in the 4th quadrant. And the y-coordinate has to be negative, because it's in the 4th quadrant. Very good so far? Now I'm going to use this piece of information, because I remember that cosine is x over r. If cosine is 5 over 7, then, well, x is 5 and r is 7, right? Everybody feel good there? Just got to find y now. What's the relationship between x, y, and r? The Pythagorean theorem. So I have x squared plus y squared is equal to r squared. So 25 plus y squared is equal to 49. Subtract 25 from both sides. Square root both sides, and I get y is plus or minus. I'm going to rationalize, I'm going to reduce this radical in my head to root 6. Now, do I want plus or minus here?
Plus.
Remember, y is not a length of a triangle anymore. It's a coordinate.
Minus.
The y is the minus. Now that I have this information, can I find any other trig function's value?
Yes.
Yes, right? in this problem, we're asked for sine. So that's y over r. Y is negative 2 root 6. R is 5. Final answer. I know I went fast there at the end because I heard you guys all packing up and I got nervous that I was like imminently out of time, and now I look at this and there's still like 30 minutes left and I felt like you guys rushed me on purpose. So shame on you guys. That's it for chapter 2. You guys should now be able to do the rest of the problem set 45 through 60. Next time, we're going to do some Delta Math practice on skills from this section. And you're going to do the Delta Math the entire time you're in here, because I want to make sure that you're getting feedback and like running into questions. The biggest thing, well, then you take it home. But like, we gotta like make sure we're getting to the hard stuff and figuring out what you know and you don't know, so you can ask something about it, right? The biggest thing is being able to effectively use this unit circle. Over and over and over and over and over, we're going to use this. Is that something that needs to go on a note card?
No.
No. You know why? I'm going to give you a copy of it with every test or quiz or whatever you might need it for. There's no expectation that that's memorized. I will give it to you, and you can take it. I have a copy for you to take. Put in your notebook next class. It'll be your copy. If you need additional copies, they're in the OneNote. Let's print off another one from the OneNote if you lose the one I'm going to give you. But you feel okay? All right. Again, today, the stuff we did. Hopefully not that bad. Hey, I have a bunch of calculators. Don't leave with my calculator.
I know you are.
This is all my
Thank you.
Thank you.
You're welcome.
Thank you so much.
You're welcome.
Thank you.
Take care, Hannah.
Thank you.
James, how are you doing?
Doing good. How are you?
Good. Adriana, don't be late to community time.